My name's Oldridge, and I'm excited to share work done by a team at NVIDIA with you. It's entitled Merlin, a GPU accelerated recommendation framework. What we're trying to tackle is some of the common industrial recommendation challenges. So things like feature engineering, where iterating over the features takes a lot longer than training to develop the data set that you're trying to train your model with. Data loading is a very common problem when it comes to training and one of the slower points in the system. And we've developed special data loaders for a number of frameworks that help really accelerate that. Scaling training, so helping fit embedding tables into multiple GPUs so that you can train models that scale beyond the size of a single GPU. And finally, helping with the path to deployment. So deploying a recommender system is incredibly challenging, and we're trying to develop tools that help make it easy to get the models that are developed in research and in your training pipeline into production easily. So to do that, we've developed the Merlin recommendation framework. It consists of three components: NV-Tabular, HugeCTR, and Triton. And they're designed to handle those problems I was talking about. So in terms of the feature engineering, we have NV-Tabular, which helps accelerate that and prepare massive data sets in minutes. And we'll go through an example there. It also supports asynchronous batch data loading, which helps keep the GPU utilized and really move data to the GPU quickly. HugeCTR allows you to use data and model parallel training to scale to terabyte size embeddings. And finally, Triton helps with the deployment into production with inference times that help support maximum throughput and apply latency constraints. It's a very full-featured inference system. I'm excited to share all three of these components with you today. So the Merlin recommendation framework, the whole idea behind this is that we're trying to develop something that is open source, that's easy to use, that's GPU accelerated, and that runs the whole recommendation system end to end on the GPU. And so we're thinking about the ecosystem and not just the training stage. And that's why we're very excited about this Industrial Recommenders workshop, because I think it's an excellent venue, and I'm excited to see people thinking about this at the end-to-end scale. So NV-Tabular is our easy to use and deploy GPU accelerated ETL. The core idea is to apply common feature transforms that you see in the Rexus space on the GPU. There's no limit to the dataset size. You're not bound by GPU or CPU memory. What we do is we apply a higher level abstraction. So you're describing what you want to do rather than how you have to do it at the data frame level or how to scale it. We support the batch data loading for major frameworks like PyTorch, TensorFlow, and HugeCTR. And what we're working on right now is kind of building an easy path to production deployment. So integrating the work done here with Triton so that you can take these systems and these workflows that you're creating in the training phase where you're building your data sets and easily deploy them into production so that those same changes can happen at inference time. Here's an example of NV-Tabular where we've basically doing a very simple NumPy or a modification of the NumPy example provided by DLRM. So the DLRM repo contains a bunch of pre-processing code to get the data ready for production. And essentially what it's doing is it's taking the categoricals and it's encoding them, it's taking the continuous variables and it's applying a log, filling some missing values and normalizing them. And so what we've done here in NV-Tabular is organize the structure of this so that you specify ahead of time the categoricals and the continuous variables. You specify the operators that you want to perform on those categorical continuous. You can also create new features that get automatically encoded as those types. And then you can specify your training and your validation data set and apply different methodologies to each. So you can keep the statistics from the validation data set separate and use the training data set statistics to update. We're able to reduce essentially what would be a 500 lines of code in NumPy down to roughly 10 lines of code. And so, this is a common reduction in code and making your workflow simpler and easier to use is one of the core principles behind NV-Tabular. HugeCTR is our accelerated training at scale model training framework. It's also open source and available at our GitHub repo. So HugeCTR is faster than TensorFlow by about 100x on a 40-core CPU versus a V100, and it's over 8x times faster than TensorFlow on a single V100. But it also supports model parallel and data parallel training to allow you to scale beyond a single GPU into multi-GPU, and we're working on multi-node. The current method of configuration is a JSON-based network configuration, and what we're working on is a Python API that helps make it sort of more straightforward to use, easier to connect with, and we're working on integration between HugeCTR and NV Tabular as well, so that the data outputs coming from NV Tabular feed directly into HugeCTR and help you create that simple pipeline. Some of the core features include the distributed embeddings to handle very large tables, so spreading that across the GPUs, an asynchronous multi-threaded data pipeline, so you can get the data to the GPU very efficiently. And we support a lot of multi-node connectivity so that you can train across multiple GPUs, but also multiple nodes to really scale systems up to the point where you're seeing a model that really fits the size that we see in the industrial setting, literally terabyte size embedding tables. So we think it's very exciting. We'd love for people to try it out and explore how it performs on their data sets. This is just an example of how the multi-node model parallel works, where the embeddings themselves get spread across multiple GPUs and multiple nodes, and then the dense model is actually exists on all of the nodes. And so we're accelerating this in both a model and data parallel methodology. Finally, we have Triton Inference Server. It's a GPU accelerated inference server. It has support for multiple frameworks. So pretty much anything that you can develop, you can fit it into Triton for inference serving. You can run multiple models simultaneously on a single GPU, including multiple instances of the same model. It has multi-GPU support for distributing the inferencing across all of the GPUs in the system. And it's very MLOps friendly, so there's metrics and monitoring and all the things you need to deploy this into production. And there's also a C library if you want to interface it directly into an application. So it's very full-featured. It's been in production for a number of years, and we're excited to be working with a team to help accelerate the recommender system models within it as well. This is just an example of Triton Inference Server on a T4 GPU, which is our inference serving GPU from the previous generation, and showing wide and deep performance relative to a Cascade Lake CPU. So you can see there's very significant speed ups in latency, and we're able to get incredible latency. And you can also, in other settings, if you check out the GitHub repo, there's examples of the trade-off between latency and throughput. And some of the cost benefits, but generally speaking, the GPUs are much more performant and reduce the overall operating cost when you're operating at scale, and also allow you to explore more options when you're doing inference. So you're able to look at more candidates and see better performance there. Wanted to demonstrate some of this with an example. And so, we've been working with the Criteo terabyte ads data set using DLRM. This is a 1 terabyte data set of ads data. It contains 26 variables, some very large cardinality categorical variables. If you take the original NumPy code that was provided by the Facebook team that developed DLRM, and run that along with running the DLRM model on the CPU, it takes roughly 5 days to do the ETL and another 2 days to do the training. So you're looking at overall 7 days on CPU. And what we wanted to demonstrate here or highlight is just that if you accelerate your training here and run the training on the GPU, you're not going to see the same kind of overall benefit when you want to iterate on your data. It's still very slow if your ETL is single threaded, and so you need to think about things and accelerate it. So, obviously a lot of people are using Spark, they're optimizing their ETL, and I've blown this up because otherwise you can't see it, it's so small. But, the ETL of the Spark CPU code, you can accelerate to about 3 hours if you really optimize on a multi-node system. So this is actually quite a large system. It's about 4 times the cost of a V100 to run, and there you can get the ETL down to about 3 hours. And similarly, if you put the PyTorch training on a GPU, single GPU, you can get things down to about half an hour. or between an hour and half an hour, depending on how optimized it is. So an hour unoptimized, probably half an hour optimized. In the next example, Tabular, we have this sort of accelerated system where we're doing all of these operations on the GPU. And so we're able to get the ETL down to roughly 21 minutes on a single V100 GPU. So, you're taking what previously took 5 days and you're running it in 20 minutes on a single GPU. And that's very important if you're iterating over and over again to try and figure out what features would be best for your system and to help try and develop, the data set and get it ready for the model. And finally, model training takes another half hour. So your overall cycle, can be on the order of an hour, which is reasonable. But what I really love about HugeCTR and Tabular combined is that you can scale things up onto a full server and get pretty much linear scaling. So what we've got is Tabular on the GPU doing ETL and HugeCTR doing the training, and we're able to scale this up so that they roughly take about 3 minutes each, and the total time taken is 6 minutes. So we've gone from from a 7-day cycle where you're getting results every week to a 6-minute cycle where you're really able to actively modify and detail. And again, this is a 1 terabyte data set, with hundreds of millions of examples. So this is not a small or trivial example. This is something we're very excited to share. Thank you so much for the opportunity to present this. We have all of the code that was used for this. All the examples are available in our GitHub repos. So there's the NVIDIA Tabular repo, the HugeCTR repo, and the Triton Inference Server repo. We're working to make this into a cohesive system, something that really is easy to use and flows. We're looking for partners to help develop it. If you're interested in this, all of the development is being done in open source and actively. We'd love to have people come out and participate in the community we're trying to build. If you have ideas for operators that you want to see covered, if you're concerned about will this work for your use case, please reach out. My email is here, eoldridge@nvidia.com, or you can reach out to me on Twitter or post a GitHub issue. Thanks very much. Really appreciate the chance to present and share this with you, and very excited to see the other talks today.